So, relatively straightforward is asking for what are the intermediates to this reaction. So they're showing a bunch of different structures, and you would have to try and nail down what those individual structures were and how they tied back to the individual reaction itself. Man, that's kind of a gross question. But hey, it's there, so you'd have to deal with it. So where should you start? What should be your first process of action? Okay, mercury. So cool. What we're hearing, or what I'm hearing, is that we should ignore the answer choices and we should focus on what we've got kind of to start with. When going through and looking at what we've got to start with, there's a couple different places to go. First off, I heard someone reference the pi bond. Okay, so we could look at the pi bond. Not a bad idea. And then I also heard someone reference the mercury. So, start with that. If we start with just looking at the pi bond, that's going to be misleading, or potentially misleading. Theoretically, what we're looking at as far as a chemical reaction, recognizing we have the pi bond might help us out that we're going to do an addition, which means during the intermediates, we would expect the loss of a pi bond. Right, which isn't particularly helpful because I believe all the answer choices showed a loss of the pi bond. Okay, so we are running an addition. What we should be really focusing on is what's going on with our individual reagents. Looking at the mercury is a good first place to look instead of step 2, our sodium borohydride, because the mercury has to run first. So what are you looking at when you see the mercury reagent? So this is going to come from what you have either memorized about it or what you can kind of pick up out of this. Mercury becomes a little bit of a nasty reagent because particularly when we draw out our mechanisms, we don't draw all the details behind it. Mercury has effectively a lone pair of electrons, okay, and it has a place to accept electrons, and that becomes kind of weird to go through and see. Ultimately, mercury, with where it's located, has access to the d orbitals, and it's those d orbital transition electrons that it's using to actually kind of donate back. I believe it was Kazaya that complained about the bromine mechanism that we looked at. This is doing something very, 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 very similar. So it's unfortunate she's not here for that. But if you all remember the previous conversation, that's one of the things that was going on. What I would argue you should be seeing is that we have this OAC in 2 of them. What does OAC stand for? This floats in a little bit of a weird gray space. If you're like, I have no idea what OAC is, there's 2 things you should be checking. Number 1, at the beginning of the book, they give you some abbreviations. Right? Because the abbreviations aren't always common, so they do provide some of that context. Right? If you don't see it and you don't know, ask. So if you don't know what OAC means, what I will go through and tell you is the AC stands for acetyl, which again isn't particularly helpful for you, but I'll draw out the rest of the structure. So when we're talking OAC, that stuff in red is what the AC is. Why does that become helpful to us? Well, when we're looking at our electrophile additions, particularly if we follow the patterns that I've been telling you to look for, the really critical piece of information that we need to be looking for to evaluate our mechanisms and therefore our transition states or intermediates is going to be the ability of a leaving group. So I need to look at my electrophile, my mercury, and be like, do I have a good leaving group? Would this be a good leaving group? Yeah. Okay. Oxygen's electronegative, and on top of which we get lots and lots of resonance. Not lots and lots, but lots of resonance. That resonance stabilizes, so we're looking at a good leaving group. That good leaving group is effectively the p orbital that I talk about in the lectures. So that's what's making the mercury act as an electrophile, and then those d orbital electrons, or the size of the mercury, is going to contribute to it providing electrons for the rest of it. Because we can recognize, if we've done that, that our leaving group is good, we're looking at a 3-membered intermediate, which means if I'm going to draw out kind of the first system, I'm going to be looking at a 3-membered intermediate with the mercury coordinated to both those positions. Mercury had 2 bonds. We're now making sure it has 3, which means the mercury in this structure is going to be positively charged. Right? If we formalize those bonds as we might need to enhance stereochemistry, we're forming a 3-membered ring. Those are officially stereocenters on our carbons, which means those red bonds should specify that stereochemistry. Okay. This gets dodgy, particularly for this question, because are they showing the intermediates where they're both wedged, or are they showing them where they're dashed? Okay. Until we actually look at the answers underneath, that's going to be kind of hard to see. But the very first thing we should be looking for an intermediate within this, or the most common thing, would be that mercuronium. Remember that onium ion, the bromonium ion? That's referring to that positive atom. Okay, so we're looking at mercury with a positive charge. It does not want to be positively charged, so it is aggressively and actively trying to break one of those 3-membered ring bonds. Which bond is going to be the easiest for it to break? Red or purple? The purple one becomes the easier bond to break. So the mercury is already actively leaving that site. That leaves that carbon, call it our purple carbon, now very susceptible to a nucleophilic attack. Okay? So what would we need? We need electrons. So that's where we would go to the rest of that step and be like, why is there water present? What does water supply?
Electrons.
Electrons. So our water can come in attack. This is going to set us up with our mercury, OAC. Where should our water be if our mercury was wedged?
Dashed.
The water should show up as dashed. Officially, that would be positively charged. Oxygen doesn't want to be positive, so very swiftly yanks the electrons off. Since we're being asked about intermediates, we might actually have to go through and show the detail of that intermediate. And we'd have our oxygen connected. What happens in step 2? Because now we would move on to step 2. We effectively have neutralized all the charges. Sodium borohydride supplies us with H-. Okay. If you haven't seen it already, boron does really gross chemistry and very repetitive chemistry that you probably want to ignore for the most part. When we're looking at BH4-, okay, we've nullified boron's kind of crazy chemistry, and we're really just seeing H-. Okay. How do we know it's H-? If we go through and look at the structure for our borohydride, we might go through and say, well, isn't the boron negative? Yes. The boron is formally negative. But is the boron a nucleophile? To be a nucleophile, what does it need to have? Electrons. Does the boron own any electrons?
No.
There's no lone pairs. Okay, so that seems really kind of counter to how we would think about it. If it's negative, it should be a nucleophile. Where are the active electrons? The active electrons are actually stashed in the bonds between the boron and the hydrogen. But now the question is, which atom owns those electrons? The boron or the hydrogen? All right, well, to figure out which atom owns those electrons, what would we need to look at? Electronegativity. And this is where the vast majority of people go, oh, well, boron's more electronegative than hydrogen. And this is where I would ask the question, is it really, though? And if we spend the time to go look it up, guess what? Boron is actually less electronegative than hydrogen, which means those electrons are spending all of their time with the hydrogen, not with the boron. This particular reagent and its sister reagent, aluminum hydride, right, are designed specifically to provide negative hydrogens as nucleophiles. Right? They will show up again in second semester. In fact, first semester, I think you really only see borohydride, but you'll see borohydride and aluminum hydride in second semester because we use them as nucleophiles. Okay, what is that nucleophile going to do? Some crazy mechanistic stuff that you probably don't really care about, but ultimately what's going to happen is the boron or the hydrogen hydride is going to replace the mercury. The complete logistics of how that mechanism works beyond the scope of what you need. Okay? So what ends up happening, that would then take us to our final answer where we've now added the hydrogen somewhere on that position, and we've added our OH. The exact relationship between the hydrogen and the OH becomes a non-critical issue, and you don't have to stress about that. Okay. Kind of, sort of. So cool, now that we have our full mechanism written out, what could we go through and do? We could go back and actually answer the question. So we go back and answer the question, and we look at all of our pieces. Note they're referencing enantiomers. Why are they referencing enantiomers? There's two products because the pi bond could have reacted where they were wedged or dashed. So you're going to end up with two of those potential products coming out of that, as long as you had a stereocenter, which we do. So we now want to go through and look at each of those pieces. If we look at answer choice 1, answer choice 1 is forming that mercuronium ion. Okay, before we get too super excited about that being an answer, we should also double check something. We'll come back to that in a second, because if we look through the rest of our answer choices, that mercuronium is screaming on a pretty good answer. We look at answer choice number 2. We have boron coordinated to it. At no point did we show boron coordinated to this. And you might say, well, that seems silly. Why did they show that as an answer choice? We'll come back to that one in a second. But that boron should be off. We look at structure number 3. We're seeing the boron again connected to the structure. And again, we'd say, why does it need to be connected to the structure? In our mechanism, it didn't do that. You're right, it didn't. Why are they showing it? We'll come back to that in a little bit. Which then sets us up with our last answer. We've got the mercury on there. We've got the oxygen having attacked. Okay, so both structures 1 and 4 are looking pretty good as answer choices. Kind of makes sense? Things we want to kind of nuance and be extra careful with. If we take a look at structure 1, 1's harder, so let's ignore 1 for the moment. Let's take a look at structure 4. If we go through and look at where our pieces are connected, we've got our mercury attached, yes. We have the oxygen attached, yeah. So that's everything's perfect. Where are they attached? Yes, they're anti, which is fine. Isn't that anti in our drawing too? Yeah, so that makes sense. That's okay. Okay, what you're referencing there is the stereochemistry of your product, which is great. That is part of this, and that is going to become important. That's not what I'm asking when I talk about where. What I'm talking about is the regiochemistry. The regiochemistry is what atom connected to what atom. If we go through and take a look at the mercury in our product here, the mercury is connected to the less substituted carbon. Where's our oxygen connected? The most substituted carbon. We go through and take a look at answer choice 4. What happened? They're in the wrong place. So what does that mean? 4 isn't right, which at this point, that better mean 1 is correct. Okay? When we pull up the answer choices, we're going to look at things in a little bit more detail as well, just to watch out for these so you can see what kind of potential tricks they might throw up their sleeves when looking at these answer choices. If we go back and look at answer choice 1, there is one more thing that we should be watching for, to be careful of if they want it to be really, really, really tricky. They can absolutely do it, but it is now starting to dig pretty deep into it. What is the relative orientation of these methyl groups? They're on the same side. Why does that become important? Could they have drawn it where it was dashed? Was it ethyl? Yeah, it was ethyl. Yeah, they could have done that. Would that have been equally valid?
No.
Why not? Okay. If you look at the starting material, identify those methyls. They're the methyls. They are cis. Because the mercuronium forms that three-membered ring in a simultaneous reaction, there is no bond rotation, which means the methyls, if they start cis, it's not Star Wars, if they start cis in our starting material, they'd better be cis throughout the entire process of our mechanism. Does that make sense? Okay. So if we're evaluating this, okay, Tyler was right looking at 4, okay, talked about the stereochemistry, which is good, but we had to move into the regiochemistry. In structure 1, we could drill all the way into the stereochemistry as well. Kind of makes sense? When do you have to drill all the way down?
When two of them are similar.
When you're looking at your answer choices and you're like, these two answer choices are different, but they're very similar, you're probably being asked to drill all the way through that entire process of that mechanism to understand the nuance between those two. That's when you answer that question. We didn't have to do that for this question, because what did we go through and do? We eliminated 3 out of the 4 possible things, which means we only have one answer that's valid. Does that kind of make sense? So we could look at it and we could flag that and be like, I'm going to have to worry about stereochemistry. Maybe. Deal with the rest of the question first. Double back if you have to. Make sense? Okay. Last thing that we needed to do before we kind of explain some of these is that if we go through and look at our answer choices, okay, in our initial pass through, we said 1 and 4 were possible. At the end, we were like, it could only be 1. If we take a look at our answer choices, you get the system where 1 and 4 is a possible answer choice. Okay? What they're testing on is, are you paying attention to the regiochemistry of how that reaction works? Or did you do something else? Okay, that something else becomes important, and that's where we'll leverage into the next aspect of why this question is kind of important, but they didn't show a practice question that allowed me to ask the question I wanted to ask. So we're going to tweak it. Before we tweak it, do we have questions about what's up there?
For step 2, you kind of just, for the OH, that's for the portion of step 2 that has the OH in it, do we just not?
Oh, yeah, you don't have to worry about the OH. Yeah, sometimes it shows up, sometimes it doesn't. I think that is technically there to clear the mercury and the boron, because they form some weird complex, so the hydroxide is there to kind of neutralize and minimize that as an effect. Other questions? Okay. Undo. Yes. Okay. Where I want to go now is erase all of this stuff. And I want to call out something that's particularly useful, particularly as we look at this particular, or this reaction. Let's see if I can say particular another 4 or 5 times today. What does the mercury reagent do? What does the HgOAC2 followed by step 2 sodium borohydride do?
You said 3-membered, right?
Okay, which is great. Knowing the 3-membered ring is fantastic to stereochemistry, but we can take a step further back to make this easier. It was addition. Okay, you could even go through and say it was electrophile addition. We could talk about the 3-membered ring. Okay, but one of the common things that you're going to be expected to do is to predict the product. So what does this reagent do? So electrophile addition, we lose a pi bond, we make 2 new sigma bonds. What are the 2 new sigma bonds you make? Say again? Yes. If we look at our final product, what we're really doing is adding H and OH across the pi bond. Okay? The mercury and the sodium borohydride are used to kind of finagle and support the addition of H and OH across that pi bond. Why call attention to this? Number 1, that's an easy thing to go through and memorize. You see the reagent, I want H and OH. Okay? ACS is aware of this, which is why they start to ask questions like this. Okay? Because this now shows a deeper understanding. Not just did you memorize what the reagent does. Okay? Why do we need to push on that deeper understanding? Because they don't actually have to go all the way into the mechanistic level detail with this. What other things add H and OH? So option A, we've got our mercury stuff. Option B, what's
what is it called?
there?
Boron with H3. Yeah, that's how.
Our BH3, and we'll have to come back to that one too. And, say again? So if we start talking about bases, and this is something that they tend to try and capitalize on as a mistake. Because you're like, oh, I'm adding OH, so what would be a good reagent to add? Why not hydroxide? Because that has OH. The problem with that is hydroxide is what charge? Negative, and what charge is our alkene? Effectively negative. That's going to be opposite charges repelling, and that's not going to fly. Does that make sense? Okay. So you will sometimes see that, but that's a full-on distractor answer. Okay. What they're preying on is you just recognizing the big changes and you're just guessing. Answer choice C actually came from the chapter that some people claimed was easy. H plus and water. H plus and water will also add H and OH across a pi bond. Okay. Why is it important to call this out? That is 3 reagents that all do the exact same thing. They add H and OH. How many answer choices are you supposed to have? 4, which means they could show you a reaction that says, we added H and OH. Which reagent did you use? And immediately they have 3 valid answers that add H and OH. Okay, does that make sense? So how those reactions work becomes kind of the next part. Okay, if we leverage into the discussion that we talk about with the patterns that I've told you to recognize, the OAC, great leaving group. That sets us up with a 3-membered ring. Okay, 3-membered ring within our transition. BH3. BH3 becomes different. The electrophile is going to be our boron, so that's the positive. What's the negative? Hydrogen. Okay, technically hydride. Okay, this one's again a tricky one because we look at it and we would immediately think, well, boron's more electronegative than hydrogen. No, it's not. And extra issue. What's the hybridization of that boron? Okay, and for people that are like, I don't know, well, if we draw it out, there's BH3. It has 3 groups of electrons. But it's missing its octet. Shouldn't it have a lone pair? No, it shouldn't have a lone pair because it only has 3 valence electrons. There's no way to get an extra lone pair in there, which means what's left over? An empty p orbital that can act as an electrophile. I can dump electrons into that spot. So the boron acts as our electrophile. Okay? If the boron's acting as our electrophile, similar to the mercury, something has to be the leaving group. Well, what's the leaving group? It has to be a hydrogen. But it's a hydrogen leaving with electrons. Is that a good leaving group? Nope. That's because it makes a 4-membered ring. I can't decide what I was trying to draw. We have a 4-membered ring for our transition state. Is that going to change the dynamics of the rest of the products that come out as far as, yeah, all of that now contributes and changes to that. Okay? If we continue on the H plus and the H2O, here you're adding H plus. That's the active ingredient right out of the gate. There's nothing special on that. It's just we add H plus to it. That forms a carbocation. Now the carbocation can be reacted with our oxygen. That's following all the standard acid-base stuff that we would also do when we're looking at acid additions. Okay, so the kind of extra piece, I guess, to remember that would be carbocations. Why does this become relevant? Each of these 3 things does something different. We don't have 3 different reagents to do one task because we feel like it. It's because they do different things. They all add H and OH, but under slightly different circumstances to force slightly different products. Right? When we talked about why answer choice 4 was wrong, why was it wrong? The regiochemistry was wrong. It's placing the oxygen in the wrong space. Okay? But that regiochemistry shows up for the boron reagent. The boron reagent places the OH in the unexpected space. Okay? Because the mechanism changes. So now the orientation of our H and OH changes locations. This is where you'll get people referencing these types of additions as Markovnikov. Okay? And I'll try to be more gentle about it, but we'll see how it goes. Okay? Markovnikov was an ancient Russian dude, I think. Okay? We're talking about 100 years, maybe, I might be wrong on that. Okay? 50 to 100 years before the discovery of an electron. Okay? So we have zero understanding of electrons. What was organic chemistry all about? What have we spent the entire semester doing with organic chemistry? Moving electrons. So Markovnikov comes in with zero understanding of electrons and just says, oh, look where the hydrogen goes. Okay? There's a meme or something where couples are like talking to each other and the wife is all pissed because the house is a mess. And the husband's like, oh, no. The coffee table is magic. Anybody seen this? Yeah, it's a magical coffee table. She says, what the fuck are you talking about? He was like, yeah, like if I make a mess, I just put it on the coffee table and I walk away, like within 24 hours, it's all cleaned up. It's amazing. It's the coffee table. And then, of course, the wife leaves him because she's the one cleaning it. Right? That's freaking Markovnikov. That's the idiot being like, oh, it got cleaned up. Okay? We should not be pushing Markovnikov's observation because he doesn't understand what's going on chemically. It's a phenomenal observation. Yeah, it looks really cool. It's magic. Okay? But magic doesn't explain the chemistry. What explains the chemistry is the motion of the electrons. And when you look at all 3 of these reactions, the chemistry is identical. There is no difference. It all does the exact same thing. Right? What you have to pay attention to is what's going on within the chemistry. You've been trained the entire semester to pay attention to chemistry. Don't break that pattern now. Or do it and just piss me off. That's fine too. It's not fine. I don't want that. But I get it. Right? So if you track the chemistry through all of these intermediates, there is no Markovnikov and anti-Markovnikov. The OH goes where it's supposed to go. The H goes where it's supposed to go. Why does the H appear to go to a different location in these chemistries? Because the H is following non-standard chemistry. Typically, when we think about H, what's its charge? Positive. When we look at the boron reagent, what's the charge on the hydrogen? It's negative. Of course it goes to a different location. It's a different frickin' charge. Pay attention to the charge. Don't pay attention to the atom. Okay? The charge will dictate where those things go. Okay? So why, again, does this become important? Well, A talks about this 3-membered ring. Okay? Take a look at answer choice B. What do we have? A 3-membered ring. Okay? So if you're remembering bits and pieces of the mechanism and start shuffling those things around, you could start drawing what's happening in structure 2. Okay? But if you've been paying attention to what I've said for the patterns behind these, H- is a bad leaving group, which means if I'm going to have the boron coordinate, I'm not going to coordinate through a 3-membered ring. I want to coordinate through a 4-membered ring. So that mechanism doesn't make sense. If we go through and look at answer choice C is following similar ideas. Okay, it's at least did some of the material properly, but again, it's shuffled those individual mechanisms around. When you add the boron to the structure, what's the other atom that's added? Hydrogen. No OH. When does the OH come in? The OH comes in the second step of that reaction to eject the boron. Okay? So if you need to be careful when looking at those pieces, is ultimately what it comes down to. It is a very commonly asked question because you get 3 answer choices right out of the gate. that can pull that off. That is a zero thought process approach for anybody writing a test question. Okay? And it can be insanely challenging. Kind of, sort of? Okay, so if there is something to memorize, you should memorize that all three of these reagents add H and OH, and you should figure out how it adds. Okay, that's a good strategy. That'll probably cover you at least one question, if not two or three. Kind of makes sense? How are we feeling? Spicy? We ready for another one? Smart work or the book? I hear which sounds like smart work. So, where we should start would be kind of generically what we're looking at within this system first. So generically, we're talking about acid-catalyzed additions. So let's start with just a pi bond. So here's a pi bond. If I'm talking about acid-catalyzed, the most reactive thing that's going to be present is going to be H+. So what happens within my mechanism? Okay, we'd form our bond to our hydrogen, conveniently pick something that was symmetric. Okay, so we now have our carbocation. Now what happens? That's when our nucleophile would come in. They actually said hydration. And if you're going to get hydrated, what do you need to do?
Water.
Talking about the addition of water. So the lone pairs on our water will then come through, react with our carbocation. We get our new bond to our water. The water will be positively charged. It doesn't want to be positively charged, so what does it do? It steals electrons from one of the hydrogens, and we would get our final answer with the OH. Officially, the hydrogen was still added there. Okay. What's the stereochemistry behind all of this? It's a mix of everything. Like this one genuinely sucks when you have to go through and deal with this one. Okay. For the most part, as it's written out in this example, it's pretty straightforward. We don't have to worry too much about it because we only have one chiral atom where the oxygen was added. Okay, but officially the hydrogen was added either on top or on bottom. Right? That's two products. The oxygen is then reacting with the cation, which is either on top or on bottom. So you get all of those possible kind of systems coming out of this. How can we really capitalize on this? Instead of reacting with hydrogen, I could react with everybody's favorite element, D, which is, nope, double bonded hydrogen? What? This does become important because it does show up every so often. It's deuterium. What is deuterium? It's hydrogen. It's hydrogen with an extra neutron. So its chemistry is identical. However, it's now different. It is a distinguishable group. Because it is a distinguishable group, when we get to our final product, we have two chiral atoms. Because I now have two chiral atoms, I have to evaluate the wedge dashes, combinations for all of those. And you get three possible products, if I'm doing that right in my head, where the one of those three is a meso compound. Can't be meso. You get four. You get four possible products. If that confuses you, don't worry about it. It's four products. Okay, and you should prove that to yourself. You should go through and prove that. Okay, so to answer your question, if we're going to try and rank these according to reactivity, we've got to go through and look at the overall system behind this and decide how it would evaluate. And if we're talking about the most reactive, we're going to talk about the speed of this reaction. Which of these steps do we think is the most critical to be concerned about? So what? Stability of what? Yeah, that first step is going to be our most critical. That's the biggest deal. Everything thereafter is either neutralizing charge in that last step, right? The second step neutralizes a missing octet. Okay, so really there's only one step that's relevant, and it's the first step. So we can ignore all the rest of these things. So what's going to help to speed up that first step? Say again? Okay. If we go through and look at this reaction, we've got a couple things to evaluate. We're looking at a reactant going through to a product. We should draw the product higher in energy because it's charged and missing an octet. Okay. So one option you suggested to speed this up would be to do what? Right? We could try and add in catalysts, but catalysts aren't going to change or look at what they're asking about. Okay? Heat is also going to be effectively a catalyst, but that's also, again, not what you're being asked to rank. You're being asked to rank the individual starting pi bonds. So we can look at a couple different scenarios to help speed this reaction up. If we look at the product, if the product is lower in energy, that should speed up the reaction. Okay? If I make the reactant lower in energy, does that do much? No. Okay? Because the transition state isn't closer to the reactant. So dropping the reactant energy really doesn't do much at all. Okay? So this is pretty useless. What about raising the reactant energy? Okay? So there's two things I could focus on. I can look at how can I make that reactant higher in energy, and I can look at how to make the carbocation that's formed lower in energy. So there's really two focal points on how we could deal with this. Okay, so how could I make the reactant higher in energy? What is the reactant doing? Yes, it is losing the pi bond. How can I make that pi bond more willing to react? Okay, so we're going to now encounter a couple different scenarios. So we could go, oh, well, if I make it tertiary. If it's tertiary, is it less or more accessible?
It's more stable.
So we're going to be careful. Okay, is it less or more accessible, the pi bond? It is less. If it is less accessible, what's happening? You're changing the transition state.
And that goes higher.
And that would go higher. Okay? So accessibility goes down. But we mentioned something about stability. Stability of what?
The intermediate.
Yeah. And if we're going to drop the intermediate energy down, what's going to happen to that transition state? It's going to drop even smaller. So if I can foresee a system that generates a more stable carbocation, that's going to increase the speed of that reaction. Okay? What else could I do on the reactant side? Because there you're talking about substitution patterns. Oops. What makes the pi bond reactive? The electrons. What would make it more reactive? What if I put more electrons near it? Let's put an oxygen here. That oxygen has lone pair electrons. What could those lone pair electrons do? Ooh, they could resonate inwards. And if they resonated inwards, what does that do? That causes the pi bond to continue to react. Okay? So we could look at not just changing the amount of substituents, which is ultimately affecting the product, but we can also look at what the identity of those substituents are to change the overall chemistries as well. Kind of make sense? Okay. Because we can't squeeze everything in here nicely. Let's just cheat. Whoop, that's not the right way to do it. Oh, I lied. I guess we could squeeze everything in here. So what do we see? So these are the reactants that we need to go through and rank. What are they saying is the most reactive? Why would the conjugated pi bond then be the most reactive? Resonance of what? If the pi bonds are resonating to each other, what's that do to the energy of the reactant? If they're resonating, the reactant energy should drop. What's that going to do to the speed of the reaction? It's going to slow it down. They say it's the most reactive. What's the other thing you have to consider?
Intermediate.
If we look at the intermediate, once one of those pi bonds has reacted, we form a carbocation. What could that carbocation do? It can resonate, which is going to do what to the stability of your product? It's going to lower the energy of the product. Which one's closer to the transition state, your reactants or your products? The products, which one's going to have the dominant effect? Products. Which is why that structure comes in as the most reactive. If we go through and look at the other ones, do we have any resonance? No. Okay, so now resonance is out of the picture, so we're not going to evaluate resonance. So we could go through and try and piece together what we would see within each of these. So between what's numbered as 2 and 3, what do we see?
Tertiary and secondary, actual intermediates,
Okay, lovely tertiary and secondary. What else do you see?
symmetry.
Symmetry is going to become less of a thing, but you're right, it's there. So you said the right words, but I don't think you answered it correctly. It's more substituted? Take a look at the second one. It's connected to how many different things? 2. How much does the other one connect to? 2. So if we're looking at substitution, they're the same substitution. Okay? But where they're substituted has an effect. And if we look at the stability of the product, we're looking at a tertiary carbocation coming out of the second one versus the third one would be secondary. Okay? So here we've removed the substitution pattern from being an issue because they're both doubly substituted. But how they're substituted is affecting the stability of the carbocation product. That carbocation product is now what's dictating the stability here, and we would expect 2 to react faster than 3. What happens in 4? Okay. 4 is doubly substituted again. Okay. So it doesn't have a pi bond resonance. I'll come back to your statement in a second. So no pi bond resonance that we'd be evaluating. Okay. If we look at its substitution, it most closely mimics this one. So comparing those two makes a lot of sense. If we go up to the next one further up, that one was a tertiary substitution versus in the last one are secondary. So again, it makes most sense to compare between these two. And we can ignore the other ones. Okay. There was a statement about resonance. Is there resonance? Okay, so there's a couple statements that we can push on. Number 1, chlorine does have lone pair electrons. Could it do resonance? Nope. Chlorine can't do any resonance inwards. We would exceed the octet on that next hydrogen. So there's no option for resonance. Okay. Another statement that one of your classmates just made was, what if chlorine leaves? Cool, chlorine leaves. Are you doing the addition reaction anymore? No. The question asked about addition, don't change the dynamic of the question. Does that make sense? Okay. So how would I evaluate this then? What we're evaluating is those common differences between them. There's no difference in charge, size, electronegativity, okay, or resonance. What comes after resonance?
Induction.
How is that chlorine inductively affecting the pi bond? Well, what can you tell me about the chlorine? In particular, chlorine in comparison to what? Try again. Actually being compared to hydrogen. They both have the same number of carbons. So what's the difference between hydrogen and chlorine in an inductive mindset? What is induction about?
Movement of electrons, electronegativity.
Yeah, it's movement of electrons, but that's dicey because you could say resonance is also movement of electrons. You have the right idea followed with electronegativity. Okay, so what can you tell me about chlorine versus hydrogen?
More electronegative.
Chlorine is more electronegative, which means what is it doing to the electrons in the bond next to it? It's pulling on them, which means the carbon next to it is like, well, shit, I'm getting my electrons pulled away. So what does it do? Pulls on those. And then that one says, well, hell, your electron's getting pulled away from me. What is it going to do? Pull on the electrons. Ultimately, where are the pi electrons getting pulled? Towards the chlorine, which means ultimately they're getting pulled into the structure. To do the addition reaction, what must the pi bond do?
Turn it to a carbon cation. So
Of course, I deleted the mechanism. What did the pi bond do in our mechanism? Break is okay. I'd like a little better than that.
make a positive and a negative.
Where did the electrons of the pi bond go? They went to the hydrogen. They left the structure. If we look at this last structure, what are those electrons in the pi bond doing? They're being pulled into the structure. To chemically react, they must leave the structure. Which means that molecule should be the least reactive. You've taken those electrons and drawn them into the molecule. To make it reactive, you have to pull those electrons out of the molecule. Okay? Good catch on the induction. Does that make sense? Do you feel better about it? Do you feel better about it? Okay. Do we have another question? Excuse me. When we're looking at that starting structure, the big deal that comes out of this is that this is an exothermic, or sorry, that's not exothermic. The other one, endothermic reaction. Okay, so if I stabilize those pi bonds through resonance, cool, that lowers its overall energy in comparison to some of the others. Okay, but if I go through to look at the carbocation that comes out of it, that carbocation is lowered more. Okay, lowering that reactant energy does not affect the transition state that much, but lowering the energy of the product, because it's closer to the transition state, has a much greater effect. Kind of makes sense? They did sidestep some of this argument because they didn't provide you this one. Why is that one trickier? It can still resonate, right? Why is that structure a little bit trickier to deal with? If you look at the carbocation that's formed here, you would get a secondary carbocation. If we looked at this one, we had a tertiary carbocation. We're now running into a dilemma, which one's more important, resonance or substitution? That becomes a really hard question to answer. Okay? And you're now floating on kind of the reactivity of those individual structures. So they dodge that by making sure it's tertiary, because now when you make a comparison between those top two, they're both tertiary products, except one is tertiary with resonance. That stabilizes the carbocation significantly more than tertiary on its own. Make sense? So there are plenty of cases where it gets a lot more complicated. You kind of just have to trust that we're not going to ask those questions. So, a little bit more straightforward because we're at least going in the forwards direction as opposed to having to think in reverse. Okay? But what we're seeing here is starting to introduce you into the concept of synthesis. Did we talk about retrosynthesis a little bit? Okay, we won't stress too much about that. The concept of synthesis and retrosynthesis is something that's going to come up in second semester, okay, depending on where you go to varying extents. Okay, I've seen they're neat. They're really like, almost like spectroscopy, except in spectroscopy you're looking at a narrow rule set. In synthesis, you're looking at all the possible chemical reactions you've talked about, which means everything from OChem 1 and everything you've covered up to that content in OChem 2. So they can be a bit nasty. So if we go through and evaluate this, which should we look at first, compound A or B? A, cool, I agree with that, except I'm gonna be a jerk and we're gonna shift differently. Br2 and H2O. What does that mean to you? Cool. Okay. So at this point, I don't know what structure A is. We said, oh, we should talk about it first. I said, we're not going to look at that. We're going to look at something that we know a little bit of information about. Br2 and H2O is addition. And because we know it's addition, what do we know compound A has to have?
Pi bond.
We know it has to have a pi bond. Okay? So if we're in a multiple choice scenario, we now have leverage into small bits and pieces of information that could allow us to navigate to an answer. Make sense? Okay? So don't just ignore information. If it's there, you can use that to help you move on. Right? Yeah, let's not leverage that one anymore. Let's go back and do what you guys wanted. Let's look at structure A. So structure A, what do we see? Not structure A. The first part, first reaction. What do we see? I know it's kind of small, sorry.
Base.
Andrew.
Big bulky base.
Cool. This is a big, bulky base. Okay, what else do we see?
Heat.
Okay, we see heat, okay, or a delta symbol. So if we're seeing big, bulky base and heat, what does that mean to you?
Elimination.
We're doing elimination, okay, and if we push on that even harder, we're looking at probably an E2 elimination. Okay? So now what do we do? Say again? Cool. So we could also say we see a leaving group in the bromine. We said it was E2, so we have to do the elimination as that bromine leaves. Okay, that elimination is going to involve the removal of not just the bromine, but also a hydrogen. Where does that hydrogen have to be removed from? A beta position, cool. Which gets annoying because, depending on how you count it, there's 3 or 2. Okay, there's 2 positions here, the blue dots, that are identical to each other. So for those people saying 2, hopefully you said 2. You saw those and you're like, those are identical. I don't need to worry about those. I just need to worry about one of them, which is cool. And then the other one is here. So we get 2 different beta positions to deal with. If we're getting 2 different beta positions, when we go through to make our pi bond, because we know we have to make a pi bond. Why do we know we have to make a pi bond? Cool. We knew we had to do an addition, so that means there had to be a pi bond in structure A. Why else do we need to know there's a pi bond? Because the reaction reagents that we're looking at says elimination, and elimination means the formation of a pi bond. So we get both of those as possible products. Those are an OR, which means when we move into the addition, we would get multiple products. SmartWork doesn't like multiple products, which means okay, so we've got to figure out which one is the more likely of those 2. So one option to consider would be the most stable. Okay? And if we drive the most stable one through, we end up finding out we're wrong. And we're like, well, what the hell? That must mean it's the other one, because it's the other one, now I'm right. No, that's not how that works. Why is it the other one? When we go through and evaluate the reactivity behind this, you said big, bulky base. Because it is big and bulky, we're now concerned about size having an effect within our overall reaction, which means steric hindrance comes into play. Which hydrogen is more accessible? The one on the outside. Because that's the one on the outside, we would predict that one to come into play because of that bulky base. You all did an experiment, right, with eliminations, where we tested a big bulky base. And which product was the dominant product? The more substituted or the more accessible? It was the more substituted. Okay? So the reality of the situation doesn't always perfectly align. This is where you have to rely on what it's supposed to do. Okay? And what's happened here is that we've picked structures that are simple, helping to drive that point home without having to make it a wildly complex structure that would then confuse and irritate you. Okay? So we get a balance between those two competing aspects. Okay, so once we have structure A, we can now navigate into the addition. So in the addition, that means we have to lose the pi bond. So our structure for compound B, as a first pass, everything should be constant except the pi bond's broken. And when I break that pi bond, I'm going to need to add 2 new bonds to account for that. Okay, the question becomes, what are those 2 new bonds? What's that?
They're 2 temporary bonds, right, with the bromine?
Okay, cool. So what you're leveraging is you're looking at that reagent and you go, bromine is the electrophile. Fantastic. Memorize that, keep that, own that, because that's going to show up in second semester and it's going to trip up anybody that didn't own that this semester. Okay? So yes, bromine acts as the electrophile, and what you've decided to do is go through a mechanistic understanding, mainly, or maybe because I've yelled at you so much about not doing a mechanistic understanding, you're going to be like, I'm going to stick to that and not get yelled at. Okay. Somewhat apologize for that. I'll yell gentler next time. So cool. We formed the bromonium, the 2 bonds with the bromine. Okay, now what? Look at the chemistry. Okay? Does the bromine want to be positive? No. So one of those bonds is breaking already. Which one?
The one on the tertiary carbon is...
Cool. We have a phenomenal leaving group. So the tertiary carbon, the more substituted position, is already going to be breaking off. Okay, so the blue bond is going to be our spot to break. But if that bond breaks, what would we leave behind?
Positive.
A positive carbon. We're tracking the chemistry. So the reactivity here isn't that I have a positive bromine, it's that I actually have a positive carbon. To neutralize that positive carbon, what do I need? I need electrons. Where do I have electrons? Well, when the bromine reacted, the other half of it was Br minus. That's a negative charge, right? Shouldn't that come in an attack? It's less an issue of too big and unfortunately more an issue of concentration. Water's in a much higher concentration. It's going to go through and do the reaction. We'll eject. We'll get our bromine at this position and our water here. Positive water. We don't like positive water, which means loses that hydrogen, and we'd have our bromine here, and we'd have OH here. Before we get too excited and say, okay, let's go through and draw on the product, do we have stereochemistry? Okay. So now the question is, you're saying, yes, there's stereochemistry. Where's the stereochemistry? Okay, I heard a couple people saying the bromine. Is that a stereocenter?
No.
Why not? It has 2 hydrogens. Those are not distinguishable from each other, which means that bromine position is not a stereocenter. So I don't have to worry about wedges and dashes there, half victories. But the OH, clearly I'm going to have to worry about that one.
So I mean, it's either wedge or dash. Because we had a... Oh, shit.
What's the dotted line? Symmetry, which means also not a stereocenter. Do you need to worry about wedges and dashes? Nope. Does that make sense? Okay. So Sometimes we have to worry about stereochemistry, sometimes we don't. Right? Could ACS go through and add wedges and dashes to all those pieces to show it? Yeah. Okay, but that's largely kind of making a problem when there isn't one. So if they wanted to see that stereochemistry, what they would probably go through and do is add an extra CH3. Okay, now they have a legitimate ability to go through and say, well, now you got stereochemistry, you got to worry about it. And we'd have to track that all the way back through.
The OH not, doesn't matter, the OH?
So in this particular structure, there is no stereo center at
There was
the,
a methyl at the end.
if we had a methyl, then we'd have to worry about it, because now both where the oxygen is and where the bromine is are stereo centers.
Okay.
So we would have to specify wedges and dashes all the way through. Yay.
But in that sense, wouldn't it just be like, say something like wedged, if you like the triangle?
So yeah, you would have to go back to where that stereochemistry first appeared, and that's where you would address it.
So, would the.
Are you saying we actually want to address it? I really didn't want to address
Would
it.
there be a carbocation that forms?
No carbocation
Okay,
forms.
so,
Right? So if you were going to address it, we'd go back here with the methyl. We called that wedged.
yeah.
Right? If we're going to do that, then our bromine becomes wedged, and our OH is going to be dashed. Okay. This one negates another potential problem with it. It's still symmetric on half of it. Because of that symmetry, I don't have to worry about even more complexities between cis-trans isomerism of our potential starting material. Kind of, sort of? Good follow-ups. I guess officially we just crossed time.